I just realized that I forgot something in the last video. So before we move on to the next one, delta H notation, you've got a reaction there, like the methanol. Just being really quick and sloppy on this one because you've got this in your notes already. And then over here you've got delta H, negative 725.9. So I told you at the beginning I was going to show you these two parts. The first part is the reaction. Well, the reaction's right here. We wrote it out. That's the chemical reaction we're talking about. And then we talked about exo-endo, and in that case, that's still with that symbol with the delta H, whether that's a positive or a negative number. So don't forget to include that in your notes with the last one. Okay, now the next one is, what if we put, instead of the energy out to the side, outside of the equation, what if we just put it in, like it was a reactant or a product in the equation itself? So if you look there in your notes, it says that endothermic, the reaction will always, or the energy will always be on the reactant side, right? It's something going into the reaction. And if it's exothermic, it will be a product because it's being produced or released from the system. So in those two examples, you see that the first one there is the formation of water gas, and the product, or the energy is on the product side, the 241.8. So since that's a product, I would underline that, or at least underneath that write exothermic, because it's on the product side. While the other one is taking nitrogen and oxygen to make nitrogen dioxide, but there the energy's on the reactant side. So underneath that energy, I would write endothermic, just so you can visualize that difference. So now if we go back to our one that we've been doing the whole time, the combustion of 1 mole of methanol, we still have our balanced equation, but this time where the energy has to go in the equation. So since I know it's exothermic, that number is going to go on the product side. So I would have my CH3OH plus 3 halves O2 gives me CO2 plus 2H2O plus, now this is a difference here, it's not negative anymore. Remember, the negative just meant exothermic. Here, the part that's exothermic just tells me it's on this side. So it's plus 725.9 kilojoules. Remember that this number is a delta H, not a delta HM. So if I balance this differently, if I had balanced this way, which most of you are probably more comfortable with, or at least more familiar with, if you had balanced this way, it wouldn't be the same number. It would have to be plus the 1451.8 kilojoules, because the delta H always has to match how you've balanced your equation. Okay, there's that one. Now in this one again, the reaction, we just wrote it out. Here it is, there's the reaction. But in this case, it's not the positive negative, it's the location of the energy. So this is on the product side, that means it's exothermic. That's what tells me that exo-endo, not the positive negative, because this will always be positive, no matter which side it's on. Okay, our last one then is, it's called a potential energy diagram. So for these ones, we're showing what, like in a graph form, what's happening to the energy. Is it going up or is it going down? Usually we write the equation right on that graph. And if it's exothermic, if it's losing energy, the graph will drop from the start to the finish because it's lost energy. The amount of stored chemical potential energy has gone down. So that extra energy has been lost. It's been given off. If it's endothermic and we're putting energy into the system, then that energy should go up as we go across the graph. So in your example there, you've got the first one, and it looks like this, where you've got magnesium plus half an oxygen, and then it drops down. That's exothermic, the amount of energy. And you notice in your diagram, that's exactly what they've labeled, that this is delta CH, and that's a negative 601.6 kilojoules. So they've not a delta HM, this is just a delta H, so it's not kilojoules per mole, but they've given you that. So on these ones, you almost always have your reactants written here, you have your products written here, and you have your delta H listed beside your graph, or beside that vertical part of your graph right there. Just erase that quick. Okay, so on the other one, opposite, you've got an endothermic reaction, so it starts low with your reactant. In that case, it's just water, and then it goes up to become hydrogen and half of an oxygen. And so now it's a delta, D, just a delta DH, and now it's positive 285.8 kilojoules. So going down, exothermic, going up, endothermic. So if we go back to our combustion of methanol, I know that's an exothermic reaction. So I would draw my graph like this. Over here, and give you all the details. That's potential energy is on that side. Down here, we call this the reaction coordinate. And all that really means is a kind of a way of saying time, or just as the reaction goes on, what happens. And I know this is exothermic, so I know my graph will start high. We're not using numbers yet, we're just giving it a rough sketch. And I know whatever it does, it's going to drop down. So I would write out my balanced equation here. So let's say 2CH3OH plus 3 O2s is going to give me 2 CO2 plus 4 H2O. So there's my balanced equation. Remember, reactants at the beginning, products at the end. And next to this, I would have to write my delta H. So in this case, remember that delta H always matches your balancing. Because I balanced with 2 moles of methanol, I have to use that double the amount of the energy in the question they told me, because that's for 1 mole, and I drew this and labeled this for 2 moles. So that's going to be a negative 1451.8 kilojoules. Just always remember to make sure that your energy matches however you balanced the equation. That's something that shows up on a test every once in a while too, that I'll see an equation like this where they balanced it right, but they didn't change the delta H. And that'll throw some kids off. So just be aware of that. So those are the 4 different ways. You've got molar enthalpy symbols. You've got delta H notation, where you have the equation with the energy off to the side. The energy can be just put into the equation, or it can be in this kind of form. But they all give you the same information, right? This still gives me my equation. It's right here. Here's my equation. You're still listing it out, drawing it there. And the exoendothermic on this kind of graph is going to show in 2 ways. One, they told me that's negative by listing that delta H. But it's also by showing this. That drop in the graph tells me that's exothermic. So essentially, if I give you any of these 4 different types, you should be able to give me any of the other 4, because they all give you the exact same information. So that's what we're going to work on for this lesson, is moving back and forth between these different methods to get familiar with them, and the fact that they just give you the same information, so that when we move on to some problems where you're presented with the information, you'll be comfortable looking at and evaluating these graphs and the different ways they might present this information to you. So in the next video, we'll go through an example start to finish, where I'll show you all 4 of the methods and just break them down, and then hopefully that'll make sense to you in the end.